Hi, everybody. We are going to be starting the Psychology of Human-Computer Interaction Part 1 on this. So first I want to start with just a brief primer on human error generally. So, and this comic I always love because it shows that despite all of our best efforts, humans still do things we're not supposed to do, either intentionally or frequently unintentionally. So it's important to remember that human error will always win. It'll always get through. So we need to design for it and expect it. There isn't a way to train or proceduralize away human error. There's a near infinite number of variables to consider, which changes also every day as our own human perceptions change. And one of my favorite analogies is that I draw from like systems engineering is how would you treat it if a pump came to work and decided to be a valve that day? Because in a lot of systems, right, that would be absurd, and we sometimes treat humans like they are just a fixed component, which leads to more issues. I also want to talk a little bit about inherent learning about environments. So this is a huge hurdle we have in HCI and in digital design, user experience design. Was a far greater problem when all these new digital systems were brought out in the 90s and early 2000s. But what's important to realize is how we as humans learn about our environments, right? When we have mappings and affordances, like is shown here, we learn how to use those partially from observation, but also partially from the inherent physical logic that we build up as we're babies and we're grabbing things and shoving them in our mouths and stuff. And those assumptions and expectations build into our schemas, which we'll get into a little bit later, as well as our mental models. So that's our kind of roadmap, if you will, or recipe for some task we're about to undertake. This also captures challenges while learning new technology. This was a huge problem I remember back in the 90s, right, where kids might be better at troubleshooting a video game or a PC than, or even like programming VCRs, the legendary famous one, right? Because we had already had a primer to digital environments and to some of those expectations and assumptions, where some of our parents or other folks that didn't have that and were coming to this entirely new, really environmental construct, they really struggled in learning some of those aspects. So I want to go into just a big overview here of human cognition and HCI. So like what we were just talking about, the digital world's not the real world. So affordances, mappings, those kind of things, we can't rely on that inherent knowledge. Mental models, we've talked about it before, but inheritance of other systems. And if you go against those, you will increase error. Now, you might have a good reason to do that. It might be beneficial for the user, but it's something you need to be aware of. And then questions like, can you train a design that is counter to those expectations? Not easily, but it is possible. For example, as humans, we can build new mental models or schemas about the particular context of this system or those kind of things. We would have different expectations, for example, from a TurboTax software to like a hospital electronic health record, right? We can have those contextual aspects. But the biggest things you want to make sure, right, is you need to design for communication and feedback, guiding the users, signposting, things we'll get into. If you design counter to human ability, you will get increased errors. So we'll get into some of those aspects in a minute, but that's basically, we have some reasonable data points and assumptions and research about what humans can do. So if you try to make them do a bunch of things that we can't do or that we don't do well, we're going to have a problem. And here's just some examples, right? These are things that human cognition doesn't exactly do fantastically, like probabilities, future forecasting, the state of the world, anything like that. Self-judgment, we're very poor at that. And obviously we have some memory limitations. Um, but all those can be actually enabled by digital design. They don't have to be hindered. So just a brief rundown of some of the psychological concepts we're going to go through. So an important thing is to just note the history. A lot of what we talk about in human-computer interaction is very cognitive, and cognitivist would be what we would consider it. And that reason is the shift. The reason for that is the shift between behaviorism and cognitivism that happened in the mid 20th century. So previous instances, behaviorism, so the subject is a black box. We have no way of understanding anything that goes on inside of it. All we can observe or interact with are stimulus and response. And if you look at historical psychological research, a lot of early studies were done in accordance with this. And that has largely disappeared, or that might be a too strong a word, but behaviorism is definitely not in style per se. Rather, we've moved to a more cognitivist view where we do realize that most subjects are still a black box, but we can abstract different concepts, and through more qualitative aspects we can get at some of those constructs. So engineering psychology, this became a big thing. Initially, engineering psychology, or I suppose we could, we're assuming that title, but it wasn't called that. But if you go back to the turn from the 19th to the 20th century, there was some interest in the humans as a component in a human machine system. This is where we see basic action studies. This is where we see some of those improvements in industrialization. And that has grown into now engineering psychology or human performance. This is an example text from Wickens that kind of captures that. But like we've talked about before, with human factors in general, there's always a surplus of different names and titles for everything. So now looking at the birth of human factors. So this won't have necessarily a direct analog into HCI, but it's an important exercise in interface. So the big push for human factors was in air warfare in World War II. So we had a problem where planes of a certain type were constantly getting wrecked on landing. And the pilots, well-trained, highly proceduralized, well-coached, would very frequently hit their wing flaps lever instead of the landing gear lever. And no matter how much training they did, they couldn't figure it out. So until somebody came in and said, okay, let's make the levers, because they can't see these levers, they're underneath their seat. So let's make them feel like what they're controlling. And just like that, the problem was solved. This is also true, we've got these wheel and actual flap levers, but even the ones on the left here where we have a square rectangular shape and then a round one, even that distinction from a textile perspective or tactile can bring some more of that understanding. And that's kind of what started it as a, hey, this is an area that's worth looking at for some of these complicated systems. So humans, especially, you'll hear this with, especially modern, our obsession with AI and things where, oh, humans aren't good at this, human error is the greatest source of error, etc. It's important to remember humans are not necessarily reliable. That's what machines have high reliability, but we are extremely resilient where machines are not resilient. And that's kind of the distinction that's important to make there. So we're going to step through some of these. So cognition, then to perception and sensation. And I believe that will close this part there. So sensation. So this is the physiological capacity of organisms that provide data for perception. So this is transduction of energy through our sense organs. Perception is that next step. So it's the organization, identification, and classification of that sensory material or data into representations within our cognitive processes. And that's kind of how we understand those things. Famous examples here, the Necker cube or the Ruth phase, where they can kind of be like optical illusions at times, and they exhibit kind of some of our control over the sense information. But I also love this quote, if you've ever seen the show Fargo. It's from season 1 of Fargo, where Billy Bob Thornton here plays Lorne Malvo, who is a hitman of sorts, and he puts on this act in the police station, and Colin Hanks' character, a police officer, goes up to him and says, how can you do that? You know, basically, what are you that allows you to lie like that, basically? And Lorne's response to him was, did you know the human eye can see more shades of green than any other color? And that's an interesting sensation and perception question. It is true. And so then we ask why. And the typical answer that psychology has kind of derived is it's an evolutionary trait. Typically, humans were in areas that were very green, and predators were also there and could hide or camouflage into different shades of green and those kind of aspects. So humans developed this ability to see greater amounts of green in order to survive in those environments. The assumption here being that Lorne is a predator. But that's still a perceptual, interesting aspect of how we do these things and why, and how some of these abilities came about. Looking at cognition, the mental action of process or acquiring knowledge and understanding through thought, experience, and the senses. It's the ability to think. Some folks might even go as far as to say this is sometimes called second order cognition, but it's a way of separation, right? So animals have cognition, but often we would say they don't have second order cognition, which is thinking about thinking. So looking at this, and this will be kind of an example of some of our perception and how our schemas and kind of our expectations start to impact that. Specifically, we're going to focus on this area over here on the left where we have a shadow there. So if we look at this area, and ask these questions, like what is that dark area on A? Are B and C facing the same direction? Are B and C on the same or on different buildings? And does the building at D extend behind the one at A? Now, just plainly, the sense information of this image would not give you the answer to any of these things. Rather, it's our perception that helps us organize and classify these things in a way that helps us make sense about the world. And in this case, understand depth and shadow and relative positioning. But that isn't present. None of that information is present in the raw sense data. And that's kind of the point to take away there. Big thing lately has been computer vision and deep learning. So here's some examples, right, of this is how we're trying to get computers to do what we do. And it's still a big struggle, a big area of research and things. Obviously, we've got self-driving car, or this could also be the computer output for a collision mitigation system here on the right. On the left, we've got a classification algorithm looking at different things there. Obviously, if you're interested, if Feel free to go dig around computer vision fails on the internet. There are some hilarious ones, but it is something that that a lot of folks are working on pretty hard. So now we're looking into a model of human information processing. So we're going to go through a few of these, but just kind of for a reference, right? This is one example of a model of how humans process information and how it kind of works through a flow. We also have another definition of that second order cognition, metacognition, which is also accurate. Wouldn't be a psychological concept if we didn't have 4 or 5 terms for it. But as you see here, we've got senses, then we have perception, diagnosis, and choice and response. And then each one of these has some other components, right? So just to start with senses, we have selective attention or cue filtering. This is the example of you could be in a loud area and be expecting a doorbell, for example. You can tune to your expectation of that, and then you're more likely to hear it, even in a loud environment. And then, we go through perception. This is where we end up in situational awareness stuff. Diagnosis. Diagnosis is typically considered, where we kind of handle that perceptual information and then determine what to do with it. So, like I said, this is one example. We're going to go through a few, but it helps to kind of understand how these processes work. Here's another example, the model human processor. So this hypothesized the brain as a computational engine of sorts. So here we have different timings of different aspects. So we have, visual capacity, half-life of visual image storage. This is in our working memory and aspects. So can be very helpful. This is also where we get the 7 plus or minus 2 rule about the amount of chunks that we can keep in our mind at any one time. You see that down here, effective working memory capacity, 7 chunks, plus or minus 2, 5 to 9. These have been largely validated through significant efforts of empirical study. But keep in mind, the just sheer differentiation of humans, as well as different perceptual shortcuts and things that we learn, but these may not be completely authoritative, but they're a good starting point to be aware of. Then we have multiple resource theory. So before this theory, there was the assumption that all human cognition, all of our cognitive resources, attention, memory, those kind of things, we're all essentially in one bucket. And that didn't ever mesh well with our experience. For example, if you've ever been trying to watch TV and write a paper that is due, you will know that that is a challenge if you, as you may start writing words that you're hearing from the television or from folks around you. And that seemed to counter the idea that there was one big pot where you're just doing 2 things. It shouldn't, outstrip your cognitive resources that quickly. So Chris Wickens proposed the multiple resource theory, that humans actually separate cognitive resources into specific sub-pots, let's say, or sub-buckets. So tasking in similar areas can degrade without affecting other areas. So my example here, writing a paper while listening to something that has text, either auditory lyrics, or even if you're trying to write and read simultaneously, can be a big struggle because they are both along the auditory pathway here. And so we run into, if you're perceiving a certain amount of auditory information, but then you're trying to process auditory information, you're going to quickly run out of resources in that way. Or vice versa, if you're auditory, if you're working on a paper, so that's taxing your auditory resources, and then you, let's say you're watching something, but it's on mute, and there is no text, or you look at art, some of those things, they don't conflict because they're along different vectors here. Then we also have the keystroke level model. This is essentially the modern HCI version of what I would call basic actions, or like the old pig iron study that were like kind of, we would consider them now like microeconomic studies about worker efficiency that was done in the late 1800s. The keystroke level model is essentially that for computers. So this can be useful, it can be beneficial to users or it can be harmful to users if used against them. But this is essentially some data points, again, looking at times of different operators. So in the keystroke level model, we have operators. Here's their examples. So we have keystrokes, pointing to a target, homing the hands on the keyboard, so like finding home row, those kind of things, drawing, mentally preparing for executing physical actions, and then system response time. So these can be, again, another useful measuring stick if needed. It can be a helpful aspect of some task analysis depending on what your goals are. But like everything else, it's a tool. It's not on its own the most authoritative thing we have. So now so we talked a little about schema as a mental model. So an important thing to realize, right? A schema is a set of, let's say, steps or triggers, cues, different things that guide our behavior in certain contexts. So for example, if I walk into a store and there is a line of 5 or 6 people, I know not to walk through the line, for example, unless I need to. I know to wait in the line, step forward every few minutes or so. I know to generally stand in the line facing forward. I wouldn't stand in it facing backwards and then taking backward steps. We learn all of those things, like I said earlier, from observation and experience. And those are what build our schemas. And schemas can be very, very impactful for us in design. If we can tap into those schemas and align our design with that, we can have greater success. So, but with that, schemas, mental models, and everything are all abstractions of how our memory works. So we won't go too deep into this, but it's important to note, we receive sense information and begin processing it. This ends up in our working memory. It's saved if necessary, erased if not. Example here is saccades. So again, if you've taken sensation and perception or some of those courses, right, a saccade is when you are staring at one point on a wall and then move your vision to another point on the wall. Unless you close your eyes, right, your movement from point A to point B, your eyes see everything in that way. But there's something unique about saccades where our brains have learned that when we're doing them, the intermediary stuff isn't super necessary. So the vast majority of the time, it just gets offloaded into the dump of our memory because we don't need it. Now, if there was something really jarring, let's say, or unexpected in the middle of a saccade, your vision would probably notify you in some way. Your brain would capture that, okay, there is something here, but the vast majority of the time it just deletes them. We don't actually see anything in that way. Our eyes sense something, we don't perceive it. And then as we go through, eventually we would encode certain experiences or certain data points into long-term memory. This is how we end up with our explicit memory, declarative memories of facts and events, procedural memory. All of those are basically they're formed from things entering working memory, moving to short-term memory. We attend to them, so we spend attention on them, which is a cognitive resource. And by doing that, it will force our brains to encode them as nodes of things that we need to do. It's partially where, if you're learning a new language and you're learning to write it, they will, speak it, write it, read it. You do repetition in order to force encode that information. So looking at schemas and memory retrievals, right? Chunks of information, a schema is a chunk of information which, when assembled, can give you a procedure or an example of an action. And so this is an example of how this works. So you sense something, pay attention to it. So this is where we're moving into perception. Our memory serves up examples from our memory that involved the stimulus we're being presented with. Then we can activate the relevant schema. So for this, a dog, and we respond depending on what our context is going to be. So that's kind of how this process works. And important for us to remember, a lot of this is subconscious. We don't actually consciously do this. We can, but most of this happens kind of on automatic process. So it's important to keep these details in mind, no pun intended. So don't forget these. Memory is very fragile. Memories can be manipulated easily and subconsciously. There's a famous experiment where it implanted memories where they took kids, or they were adults, if I remember correctly, that had said that they never got lost in a mall or a department store, and then through some subtle nudging and manipulation, they created memories that were highly detailed. So we have to be aware of it can be a double-edged sword. So for us in designing, right, memory alone isn't enough. So we use recognition over recall. We don't expect people to remember the things. Especially in computer systems and different digital systems, we can save that for them now. We don't have to require them to remember these things all the time. So we design for that. All right, that's all for part 1. Thanks for watching, and we'll finish up psychology of human-computer interaction next. Thanks.